Oh, hi everyone. This is John Avina. I'm here with David Jump, and David has been around for, I don't know, probably longer than me, so a long time, 30 years. He's got a PhD. He's super smart, and he's been uh, heavily involved in EVO and in, I believe, in the utility sector and what they call NMEC in California, and how they're developing all of, well, NMEC is he'll tell you about, but how they're using Option C to do M&V for utility programs. But he's also been involved in writing a lot of the EVO manuals as well. And if I'm wrong, David will tell me that, but that's or tell you that, but that's my understanding. But David, he knows a lot, and he's a heavyweight in the M&V business. So that's David. And he's going to talk today about using Option C in the utility sphere. It's way different. They have different requirements, different needs, and it's so much different from the ESCO sphere. So that's why I thought would be really interesting. In the past, I've written articles that have just said that we shouldn't maybe listen. ESCO people maybe shouldn't listen to utility people. They come up with all these rules, and maybe they don't really apply to us ESCO people. But on the other hand, they've done a lot of thinking, a lot of really sophisticated thinking, and a lot of the things they've figured out would be really useful for us to incorporate. And that's why I really like listening to people like David. So, David, why don't you tell us more about yourself, and then go right at it, go into it.
Sure. Yeah, I've been around energy efficiency, basically utility world in California for practically my whole career since I was a postdoc at LB&L. I came to KW Engineering, where I am now, about 8 years ago, right when NMEC was starting up. Legislation was passed that enabled utility programs, efficiency programs, to offer incentives based on changes in whole building energy use. And I thought that was great, and we're going to talk about that a bit here early on. But yeah, I've been just really trying to promote this whole industry doing whole building M&V. I was involved in ASHRAE Guideline 14, the 2014 version as well. I helped write some of the BEMP M&V guidelines when I was at my previous job at Schiller Associates way back in the day. So maybe some of you recognize me from then. But anyway, enough about me. Should I just get going?
Absolutely.
Okay, let's just dive right into it. I really like how John set this up. What can we learn? What can the non-utility world learn from what we're doing in the utility world? And I'm not going to claim to know everything about what's going on here, but I think I know enough to provide you some insights. So I want to give you some background first and talk about Option C, just to highlight a few things that I think are important before we get into the real point of the examples that I want to show you. So anyway, NMEC was enabled back in 2015 when the legislature in California passed AB 802 and defined this term, normalized metered energy consumption. And there's two flavors of it. One is site level, one is population level, which we'll get into. And site level is basically Option C. So I'm assuming, like John said, most of you out there are already familiar with Option C from the IPMBP manual. There's 4 options, A, B, C, and D. This is where you take utility data and you do building analysis, essentially, define your baseline models and so on. We'll get into it. But anyway, in the legislation, it highlighted a couple things that made it distinct from the current program offerings. So it's a program for existing buildings, and it's for all estimated energy savings, which means 2 things. It means all measures that create energy savings and above existing conditions baselines. There's no code level baseline to worry about really in NMEC, or in the M&V of NMEC, which lines it right up with Option C. It also defines this BRO term, behavioral, retrocommissioning, operational measures, which are also enabled through the program. Anyway, so that's the enabling legislation. There are basically the CPUC defined it as 2 types of NMEC. There's a site level type, which is basically Option C. Then there's population NMEC, which is based on Option C. So I just highlighted the differences here. I'm going to assume many of you are familiar with it. Site level MX is savings at the project level. You know, you're doing the analysis, the M&V analysis for a single customer. The M&V methodology is flexible. You know, you can have different modeling algorithms. You can have different time intervals. We've traditionally been accustomed to billing analysis, which means using monthly bills, but now we have AMI data, and I want to get into that a little bit. So you can use weekly, daily, or even hourly models. I think in the future, we're going to go toward hourly models because we're looking at the time value of your savings on an hourly basis. Only site data is required. So your electricity and gas data, your dependent variables, and any other variables that you can get from the building, you know, along with temperature, used in your models. You know, non-routine events, you'll see this acronym a lot, are often occurring and causing problems in Option C analysis. So we've had a lot of experience with that. And that's the main point I want to talk to you today about, or just give you some examples of what we're doing about non-routine events. In starting up programs, it's pretty streamlined on the site level side, because you're pushing all that planning for M&V off onto individual projects. And so the operation requirements of the program are a little bit more detailed. But lately, population MNEC has become really popular, and you'll see why in a minute. You know, we're talking about savings at a program level. So you can get an implementer or aggregator to recruit a bunch of customers of similar building types, and that becomes their treatment group. And you're going to quantify the savings for that treatment group. But you're going to have to subtract out the exogenous exogenous effects of comparison groups in that whole scenario. So the M&V methodology has to be the same for all the sites to be statistically valid and get valid results. You can't be flexible about how you treat it. You have to use the same algorithm, same time interval, same independent variable data for all the sites in both the treatment and the comparison groups.
And David, does that mean the same balance points as well? Or maybe
I would guess, yeah, if that's part of your, maybe like you're using a change point or heating degree day, cooling degree day. Yeah,
right.
It can be, yeah.
Okay.
So it's much more data intensive. You're looking at a lot more buildings than just a particular subject building. But using that comparison group is a really good way to account for all the exogenous effects. So if you have something like a pandemic that affects a lot of buildings, a lot of similar buildings undergoing the same kind of impacts as your treatment building, you know, this is a really good way to account for that in your savings analysis. But there could be other exogenous effects like trends in the economy, the local economy going on that affect energy use in your building. So the pre-program startup is really a lot more detailed. You have to get a lot of data and decide how you're going to define similar buildings, your comparison groups, you know, how you're going to prepare all the data and how you're going to go about it, and then document your M&V plan, which you'll stick to throughout the program. But aggregators like it. You know, you see a lot of positive feedback from aggregators who implement population in their programs because they don't have to do all that M&V analysis themselves. Generally, you know, the M&V group is some consultant that has good experience doing population NMEC that could just be, you know, part of the program administration team. Moving on from there to just a level set where we are when we're talking about option C, just real quick what option C is. There's an avoided energy use scenario where you might have energy use over time, and you have 3 distinct periods where you have energy use. In those periods, you know, a baseline period, an installation period, and a post-installation period, also known as a reporting period or a performance period, where hopefully the energy use has gone down. So the first step you do is build a model and then make predictions in the post-installation period of that model. So you can compare your energy use, what your baseline would have been with your actual use, because you want to determine your savings on an apples-to-apples basis. And I put an asterisk in there because that's really what we're going to talk about. That's valid if the conditions of the building don't change. John hinted at that in the blurb for this webinar, that often conditions change, and so then what do you do? So I think we've learned a few things that we could provide back as feedback to the industry about what we've done. Hopefully that's helpful to you in your projects. So anyway, the savings are the difference between those two. Normalized savings are very similar. The only difference is you've defined a normalized conditions period and you're making a baseline model. and a post-installation period model, and predicting under normal conditions. And the savings between that are the normalized savings that we report in these utility programs, or the NMEC savings. Just a quick illustration of population NMEC. You determine the gross savings from a treatment group. So for every individual in that treatment group, you determine the savings using the standard and static M&V methodology and sum it all up, and you get the total gross savings, or the average gross savings of the two. But then you have to develop a comparison group to figure out what the exogenous effects are. So you still have your treatment group, but you also have a comparison group of buildings that are similar to that, which represent how the impacts of whatever exogenous effects going on those buildings that haven't been treated. And so the savings you actually report under a population approach is the net savings, and that's net of exogenous effects.
David, do you do this exogenous, this comparison group in that treatment, even if there is nothing going on like COVID, or you just do that anyway?
Often, that can happen. That the exogenous effect can be very minimal, and so it's negligible. But generally, to do a true population NMEC, you do have a comparison group, and you go through this activity.
That's pretty neat. Okay.
It's not new. It's been something that's been used in the residential sector for ages. It's called billing analysis. With monthly data, it works really well. The latest, I don't know, in the last 20 years, 10 years or so, it's creeping into the commercial sector. Initially, it was thought to use population approaches in buildings where doing the full M&V individual building process was too expensive and too cumbersome in like small and medium-sized commercial buildings. So population NMEC is a good application there. But we're also seeing it in the larger commercial buildings as well. So back to site level NMEC, there's definitely advantages and disadvantages in using it. The advantages are it's based on one flexible method, just option C, same kind of methodology for each building. That's thought to free up some of your resources, and you don't have to make individual estimates of savings for individual measures, which can be very time consuming and cumbersome to do. It enables a pay for performance approach. So you basically shift the risk to the customer and pay them based on the savings they actually achieve. So that's protecting ratepayer dollars in that scenario. And also in the last, 20 years or so, we've invested a lot in putting in smart meters, advanced metering infrastructure. So we get AMI data, so 15-minute electric, or hourly or daily gas data. That gives you faster feedback on how your building's using energy. That's very useful information. So you get more insight on the building operations, and you can focus on what's really going on and maintain use. So we're seeing AMI data used in dashboards that tell you how you're using energy, and flagging problems so that you can actually make your energy use something you could better manage in your building. So that's becoming more and more popular. For site level NMEC, of course, there's disadvantages. You could have changes in the building conditions. We've seen this a lot through this COVID period. People actually changed their operations. They increased, they lowered occupancy, or maybe they increased it, or maybe they changed their operating hours. There's non-routine events. There could be maintenance downtime and so on, things like that. That you have to go back and figure out how to account for. And again, that's what we're going to get into a little bit later. It's also a longer wait for incentives. We have to wait 12 months to get a full year of data before we can do a final savings analysis. And oftentimes, customers are not interested in waiting around that long to get a payment, an incentive payment. And also, we're not seeing, we're often seeing savings not meeting expectations. So you have to figure out what's going on and why forecast savings up front were not met after the final savings report is done. So just contrasting a little bit, the advantages of AMI data. In the past, we had monthly billing analysis. You only get 12 points a year to make in general, to make a baseline model. Generally, the the models are linear regressions, something very simple. The less data you have, the less accuracy your model is. And also, if you have any non-routine events in your building, it's hard to detect in monthly billing analysis. And if you do detect them and you need to address them, it's usually a separate engineering type calculation to estimate them and remove their impacts from your M&V analysis. But we have AMI data, so more data means to get better insight. Just plotting it out is helpful. You can see, unusual behavior and operations. Maybe your chiller is cycling or something, or maybe you have unnecessarily high base loads or high peak loads. And the chart on the right is something we just on a project that we've been working with recently. We got negative savings in our site level NMEC analysis, and that means that the reporting period energy use went up for some reason. And so when we went back and used that AMI data to make load shapes, this is like the average daily load shape on a Tuesday in winter months, for example. We see that for some reason due to the measures installed or some change in operation, they seem to start up earlier, a couple hours earlier than they were in the baseline period. And although we achieved savings throughout the day, as shown by the orange line being under that blue, that wasn't enough to make up for the losses in efficiency by starting up too early. So that could be the AMI data I'm saying could be a very valuable tool to make comparisons like this and diagnose what's going on in the building, give you some insight about what's going on. So M&V with AMI data is going to be more accurate. You have a lot more data points. More data generally means more accuracy in your models. The modeling algorithms tend to be more advanced, not a whole lot more advanced, unless you really want to, but a little bit more advanced. You're going to get better accuracy, but also the possibility of using shorter monitoring durations. Maybe you can make good energy models for your baseline or reporting period with a shorter duration of time. All you really need to do is have a whole cycle of operation, your highs and lows of energy use in a year. And maybe you can achieve that in 3 or 6 months and not have to wait 12 months to pay off your incentives at the end of the day. So it's a possibility. If you have, sub-meter systems in your building, you can apply this methodology also to those sub-meter data. The advanced analytics I'm talking about, there's the familiar, which we know and use in monthly analysis, which are basically linear ordinary least squared regressions. But there's some more advanced ones. There's still regressions. There's Ashray's family of change point models developed by folks at Texas A&M. There's an example of one out at the right there, a 3-parameter cooling model. But there's also one from LB&L that incorporates the time of week into its model. So it's a model that is very appropriate for regularly scheduled and temperature sensitive buildings. Regularly scheduled that, it's generally occupied during Monday through Friday during the week and not on weekends. That model is very good at recreating those patterns and predicting those patterns. But there's no reason you can't use even more advanced type models, machine learning type models, gradient boosting machines, Bayesian methods, and so on. As long as you can test for model validity and use it, there's no reason why you can't use any modeling of it. So how do we judge models? In the NMEC rulebook in California, we have to make sure that the bias error and the random error are minimized. They're measured by these metrics, the normalized mean bias error and the coefficient of variation of the root mean square error. Really, the CVRMSE is kind of the metric that we focus on because it tells you how much random error, how well your model actually predicts your data. There's a third one, the R squared. That really just tells you how much explanatory power your independent variables have on your dependent variable. But it can be very low for buildings that don't have a lot of variation in energy use, like maybe a data center or something like that. You can make a perfectly fine and accurate model for those, but your R squared is going to be low. So R squared should not be a disqualifying factor. So we use it as guidance more than a requirement. But probably the best thing to look at is the uncertainty. So if you have a baseline model and forecasting a certain amount of savings, then you can look at the uncertainty. ASHRAE guideline 14 has formulations for looking at the fractional savings uncertainty that's really popular for use. There are other methods as well. ASHRAE's criteria is, that uncertainty has to be less than 50% at a 68% confidence interval. In California, we bumped that up to a stiffer requirement, the 90% confidence level. So you can, when you pre-screen a building, look at the uncertainty of your forecasted savings to decide if your model is accurate, if you're going to have a robust estimate of savings at the end of the day. It'll also tell you, how high and how low you can, how low you can go really in savings before your uncertainty is too high. There are risks with option C. One is the building's not predictable, so the energy use is not explained by weather, schedule, or any other independent variable. Your modeling algorithm might be insufficient. There might be too many NREs going on. So it's really important to pre-screen your building before deciding it's a good candidate. Because when you get into an NMEC project in California, you're really engaging the customer for a long time, up to 2 years. There's a 12-month reporting period after all the measures are installed, often between the time the project application is signed and the measures installed can be up to a year or longer. The rule book allows 18 months. So it's really a commitment you're making to every individual project to engage with them over a longer time. So you want to make sure it's a good candidate up front. And doing them a few times gives you the experience to make assessments on what makes a good candidate building. There are tools out there that you can use. KW Engineering puts out NMECR. It's in the public domain. It uses the R package, which is also public domain software. It uses a number of modeling algorithms, including Elbinel's modeling algorithm. We put it out there so people can use it and give us feedback on it and improve it over time. And it's open source. And it's really out there just to promote the whole concept of NMEC, using NMEC for efficiency programs. A really good precursor to that was the energy charting and metrics tools made by Bill Coran. We have a webinar here at one time, I think last year sometime. It's still available on SBW's Consulting's website here. It's an implementation of change point models. It's an Excel add-in. And then there's a lot of fee for software type tools available out there. There's OpenEE Meter from Recurve. It's an implementation of the CalTrack methods. I really don't know the costs or anything about it, haven't used it. I have used Energy Explorer way, 10 years ago. It was really great. It did the change point models. It's made by Professor Kissick, who was originally part of the ASHRAE Research Project 1050. That really kind of boosted this whole activity for whole building M&V. All right, so finally going to get to, that's all background. We're finally going to get to some examples of how we handle when your conditions aren't the same because you've had some sort of non-routine event going on in the building. So non-routine events are changes in building or its operations, and they're not related to the measures or not regular driving factors of your energy use like temperature or schedule or something like that, regular operating schedule. Some examples are temporary shifts in load due to maintenance, equipment shutdowns, that kind of thing. They could be constant load or variable load shifts. Really have to visualize it in your data and see what's happening and really get with the building operators and understand what's going on. Because you're really not going to see it in your energy data unless it's really significant. Little minor things generally you can't control for, can't detect. But the big one that we've had to deal with, whether it affected the baseline period in some projects or the reporting period in other projects, are impacts of COVID. And COVID caused a shutdown, which reduced occupancy and lowered building energy use in those buildings. Some of them reduced their operation schedules, and places like schools, they increased the ventilation, like maybe they propped over the economizers to get more fresh air in the building or ramped up their variable speed fans to higher volumes of airflow to increase that ventilation. There are various methods that are out there. EVO puts out a non-routine event and adjustment application guide on its website. Here's a link. I believe that's just to the table of contents, but you can go to the EVO World website and find the NREA application guide. And it puts out several ways to detect and to resolve non-routine events impacts in your option C approach. And we're going to talk about a few of them now. One of them is, and probably the best one I would say, is to add an additional independent variable, whether it's an indicator variable or a continuously varying variable, or use a mini model approach or a QSUM method. But there's other ones. You'll have to go into the guide to look at that. And then I want to talk about granular profiles, which is a recent technique used in population NMEC methods that really did well in explaining impacts of COVID and other exogenous effects. So getting into it, here's an example of a building. It's basically a lab building that had some maintenance shutdowns or equipment shutdowns early in the baseline period. And you can see they're fairly constant load shifts. And so we ran this. If you run this without an indicator variable representing those time periods, you're going to get a blue line that's somewhere between the lows and the highs of the data, the orange line. And when we added those indicator variables, you can see that it lined up a lot better and modeled those impacts pretty well. So we'll use that indicator variable in our baseline model and probably, calculate normalized savings without these shutdowns. But if there are regularly occurring shutdowns, we could easily program those in and calculate normalized savings with those shutdowns in there as well. So it's a very convenient way to handle constant load shifts in your building. Here's another one that takes a little more explaining. We got into this large building and made a baseline model, and all systems go. The application was signed. We started installing measures, and then the COVID shutdown order hit during the installation period. And suddenly the energy use in the reporting period after all the measures were installed is really low. This chart is of the baseline data. You can see we got, an okay R squared, an acceptable CV RMSE. The building itself was a large public office building with an attached public theater in it. And as a result of the shutdown order, they closed the theater operation for the next year. So that's the cause of the lower energy use. The public office portion of the building, which is probably 80% of the building, didn't change its operation, just the theater. So when we saw this effect, we started asking questions of the operators and found out that they had variable speed fans in the theater controlled by VFDs, and they trended that data and stored it in a historian. So I realized that that's not always available in every building, but we were fortunate it was in this building. So we could collect the air handler fan speed KW data for all the fans in the theater and add them together and average them and use it as a continuous variable that was basically a proxy for the occupancy. And then we went back to the baseline period and added that in because prior to COVID, the occupancy in the theater varied a lot. There were practice sessions, there were events, there was unoccupied periods, and added that variable in and improved the baseline model. So adding that in, you can see that the R squared improved, the CV RMSE went down a little bit. If you compare between the traces of the data and the model predictions, the blue and the green lines, you can see that with the new variable, you get a lot better matching there. So that improved the model, gave us more accuracy. And so after the measures were installed, we used that occupancy variable, and we saw that indeed without the occupancy variable, we would have got that black line as the predictions of the baseline model in the reporting period. With it, we got the blue line there, which corrected in the direction we would expect, and so we eliminated the impact of COVID there. Got a better estimation of the actual energy savings. So that's sort of an example of using an additional variable in your model to represent an occupancy. We've used other proxies for occupancy in other projects, and some examples of what we've used are key card swipes. So it's amazing that this data is actually available. Start thinking about it. Maybe you have a secure building. From the building security system, you can get the number of key card swipes per day. That's a good proxy for occupancy per day in your building. So you can actually get granular data on occupancy. Who would have known? Wi-Fi connections per day from the building IT network. That's one we used in a different project, and I just explained the one we used for variable speed fans in the theater. Yeah, and you know, the other requirement is that you have that data throughout your baseline and reporting period data, which is often kind of difficult to get, not very common. But there's other methods that you can use, and one that the guide puts out is this mini model approach. This is a recent project also. It's actually an ESCO project, and they recommended a number of efficiency measures as well as installing a solar PV system in a building. But that PV system, that building had a regular utility meter, not a net meter. And when you install, you know, a PV system that starts generating, naturally the energy pulled off the meter is going to go down, but that's not actually what the building uses. What the building uses is, you know, the energy delivered by the meter plus the solar generation less what's delivered back through the meter. And that energy meter will tell you that delivered and received data, and you also need the solar data. But in this case, we didn't have the received data. So you can see the orange line once they started the meter, that's the meter data, and it dropped when that solar data started up, as you would expect. But that's not what the building used. So to estimate what the building used, we recognized that there was a time before the reporting period started and before that solar generation started up. There were about 6 months of data that we could use to make a mini model. So we did, and we predicted over the time after the solar meter started. That's that green line.
I want to interject, right? I want to interject right here. So this mini model training period, I'm pretty sure it happened after all the other ECMs were installed, but the solar hadn't been installed first. So the mini model is post retrofit data before the solar. That's kind of important to make sure that that's clear.
Yeah. So what we're saying is, what's the energy use? What would the energy use have been had the solar system not started up? That's the question we're asking. Just like we would in option C, where we ask, what would the baseline use have been had you installed no measures? It's the same concept.
I want to interject one more thing on this, because I really like this method. This is brilliant, and it's something that I wish we ESCO people would have thought of 30 years ago. So let's say you're doing a performance contract and you have, let's say, 2 years of post retrofit data. And you know, it seems like there's not really any drift. The building's using about the same amount on year 1 and year 2 of the guarantee period. But in year 3, all of a sudden, you have 2 months that are really weird. They're just outlier months. It's really high. I don't know why. And then it goes back to normal. What can you do? You can use your year 2 and make a mini model on year 2 and use that mini model, what that predicts the baseline would be from that year 2 mini model, to then say, okay, this is what the year 3 actual should have been. Or actually not, I'll say it differently. You can use that to create the non-routine NRA, non-routine adjustment, or what we call baseline adjustment. So that's what's really cool about this. Rather than, you know, coming up with some story, it's like, oh yeah, they did this, let's estimate, I think it was this many, whatever, and I think they used this much per hour, and I think it was this many hours, and you come up with some number. It's better to actually use real data to come up with this. And that's
the caveat is that you're covering all the range of conditions in your model training period, you know, so you can have some assurance that when you make predictions that you're covering all the possible conditions there. You're not extrapolating, as we said at the top. And there's one other approach, a QSUM approach. Here is a building where, again, we made a baseline model. It was pretty good. We started, the customer started installing the measures, and then COVID hit in the middle of it. And so what we did was made predictions over the installation period and the reporting period. But during the installation period, you know, if you do a cumulative sum of savings and add them up each day, that's the green bars there, you can see the rate of savings due to your measures. And so they started installing measures, they started creeping up in savings over time, and then COVID hit, and then people left the building. You can see that blue line just drop a lot right there because they're using a lot less energy in that building, and the QSUM slope changes accordingly. So the latter part includes both the effect of the QSUM and the measures that were installed. And so to make kind of a first order approximation of what the actual savings is and to reduce the, you know, the impact of the COVID, we just looked at the slope of those lines. The initial slope was due to the savings due to the measure, and the second part was the slope of the line including COVID. And so we subtracted one slope from the other to just get the COVID impact. And then we added that back into the reporting period data and then developed our reporting period model based on that. So that's another method you can use to remove that impact. And these methods, the mini model method, the additional variable, and this QSUM approach we've used, it's been pretty successful. And I would say, you know, 80% of our projects, we do like 25 or so of them a year. The method that I want to talk about from population MNEC is called synthetic controls. And so in that approach, I just want to talk about the concept initially, and then show how you could use it to account for an impact like COVID, a exogenous effect like COVID. Say you're doing a project in a large commercial building, and so your treatment group, if it was a population program, would be another group of commercial buildings that are very similar. But you can also, and I, sorry, got ahead of myself a little bit. So what you do is you take a large group of those similar buildings and get their AMI data and determine their load profiles throughout your baseline and through your reporting periods, and average them together essentially, and that creates a granular profile. So you'll hear this term also, granular profiles. But you know, maybe your particular building is also similar to like another type of buildings like city halls, and I'm just using office buildings as an example. It could be, you know, any type of building. Define similar buildings, like maybe a group of convenience stores might be similar to a gas station or a grocery store or something. You can test this out if you can get the data. Just develop granular profiles from each one of them. So I have commercial office, city hall, corporate headquarters, developing another granular profile. And then you just put it right in your baseline model, a linear regression, temperature, these granular profiles. And then when you do a regression, you test for the significance of your additional variables and keep the ones that have some influence. You know, those coefficients might have a t-stat that's higher than 2, for example. It means they do have some explanatory power of your energy use in your particular building. So you do that for both your baseline and your post-installation, and you know, use that. You know, once you have your models specified and set, you use that for your savings analysis. So, you know, it's synthetic because you're talking about a particular building that's maybe similar but not quite like the other buildings in your set of granular profiles. Those granular profiles also capture what's going on in that group of buildings, and so you're kind of capturing that exogenous effect right in those granular profiles that you're using in your target building. So this is kind of a cross where site level and population MNEC meet, kind of in the middle. But you know, it's hard to get those granular profiles together. You need all building data, and you know, that's a lot of extra work, as I was saying up top. But it is a way utilities can actually help the industry And for example, PG&E has done this. They've taken, their utility data for their customer base and developed, residential and commercial building granular profiles. So they've published this on the CalMac website under customer load shapes right here. And so you can actually pull them off. And it's kind of a nice way for utilities to help the industry. They can publish these granular profiles. It means they don't have to share, identifying information about individual buildings to people who, to outside parties. They can just do this analysis internally and publish these granular profiles. So I encourage you to review this website and check it out and see if it's helpful for you. So just to wrap up here, just to restate some best applications. We want predictable buildings to do a good NMEC project. Typically, they're weather sensitive and regularly scheduled, as they are in the commercial and residential sectors. You want deep savings, and often that means multiple and interactive ECMs that affect many systems. So both lighting and HVAC type projects and controls are very good. You want your savings above the noise, so definitely get multiple projects in there that are going to show above the noise. How much above the noise is really what you're going to do when you pre-screen the building up front. Look at that uncertainty criteria. It's also good for projects that are difficult to quantify, like retrocommissioning buildings or doing duct sealing or envelope upgrades and things like that. So it really reduces the overhead cost of estimating some of those more difficult to quantify measures. So anyway, that's it for me.
So first one I have, which I think I hinted in what I wrote on LinkedIn, but I don't think we've addressed it, is when this NMEC thing first came out, the state, first off, the legislature in California required this. And I think it was a shock to a lot of us in the industry. Is that right? Or I think it was a shock. I don't know. Maybe I'm wrong. But and what I heard from some people is that they didn't really know what they were asking, and that the CEC and the California Energy Commission and all these consultants are going to have to figure out how we're going to make this work. And I thought there was a bit of pessimism. I know I had a lot, saying this is impossible. It's not going to work. How has this gone?
I think it's a learning curve. Yeah, there's some initial sorting out between what's really population and what's really site level NMEC and what goes into it. And the idea going into it is like, well, this is great. We can measure the effects of these efficiency programs in a way that the customers perceive them, which is based on your meter data, not individual savings calculations. And the thought, maybe it was somewhat naive at the beginning, saying, well, if you put in these measures, you should see it in the whole building data, and if you can account for all those other factors, So I think we went in as an industry and said we can handle these issues and quantify them, but some of them have been intractable and haven't matched up, and some program timelines are so long that buildings do change. They do change in operations over time. So we probably have some catching up there to do on how do we adjust for all that to do. I think some of the recent evaluation studies that I've read do show that customers appreciate and like this approach because they're more in the driver's seat. They're getting better feedback,
Right.
Often, sometimes, often the NMEC savings result is lower than what's forecasted, but is that really a problem of the NMEC analysis or the forecast analysis?
Right. That's right.
So there's a lot of questions like that, but I think, having a program framework like that forces us to look at and come up with solutions about. So I'm not going to say it's perfect or anything. You have to go into it eyes wide open and recognize, what issues you're going to have to address.
Okay. Yeah. So because a lot of ESCOs have been, over the last 30 years or 20 years have been shying away from option C because of the risk, because of the non-routine events. And so then the utilities are coming into it. But I guess you have less of a non-routine event issue because you're only looking at it for a year. You don't look at a building every year and give them a check every year for savings. It's just 1 year, and then again, incentive check based on 1 year of savings. Is that correct?
But yeah, pretty much. I mean, there's some 2-year programs that we are working with that,
Okay.
check in the second year if savings are persisting, for example, because that's a question that we need to address.
It is. Yeah.
Our company actually is engaged with customers over time, and we do look at savings year over year. And it's never just one analysis. It's like, you know, and actually the more important thing to do is probably making sure those measures are still performing. So if you have a controls-based measure, you want to make sure those control settings are not changed. They're still meeting the needs and, generating or being efficient.
Um,
Anyway, yeah, I don't know if I really answered that question, but go ahead.
do you guys, does KW, do you do any, I don't think you do any of these programs where like you look at just hotels and then you put in just ECMs for hotels and then you measure it with NMEC. You don't have any programs like that. Is that correct?
We do have third-party programs. We work
Oh, you
in the
do?
grocery sector and the lab sector.
Okay, I didn't realize that. And so then, when you come across a building where the data is really bad, you can't come up with a good model. Do you just not throw the building out or throw the client out? You do. You just say, look, I don't think we can do this one.
Yeah, we don't want to lead a customer into something we don't have confidence is going to lead to their satisfaction. Not at all. So yeah, if we get that, then we'll redirect them to another program if incentives are high on their list of priorities.
So this is just a question. I'm not trying to get anywhere. I'm just really curious of what you think. So ESCOs, you probably know this. They'll do a performance contract. They get a client. Let's say it's a school district. So there's I don't know 100 meters or 200 meters or so. They don't look at all the meters before they sign the contract, or maybe they do, but they don't look at all the meters before they decide they want to go ahead. They just assume, yeah, most of these they're gonna be fine models, but you'll run into some that are not. Yes, they can have extra variables for the school calendar and all that stuff, but some meters just aren't going to work well. They're not going to have good regressions. And so what the ESCOs have been doing for the last 20 or 30 years is they just say, okay, forget weather normalization. We're just going to compare the old bills. We're just going to use, whatever, that year's bills, and we're just going to compare it to that year's bills. And that's how we're going to decide their savings. The MX or the utilities won't do that or don't do that. Is that correct?
No, that's not. There's a rule book, an NMEC rule book, and yeah, that rule book will prevent just.
And tell me, what would be your critique of that? I'm just curious.
Or just comparing bills?
Yeah.
Well, like you said up front, you might have a mild year initially and then an extreme weather year the next year, and you're not comparing apples to apples anymore when you do that. So the savings may not be the true amount.
Okay. There was an ESCO that I spoke to. I mean, they got bought by a company, they got bought by a company, they got bought by a company, but a long time ago, I was trying to sell them metrics, and they're like, no, we just compare bills. We don't do any weather normalization. And I said, but what about, exactly what you said, the weather changes from year to year. You want to get a good picture of savings. He said, look, we do projects all over the country. If it's hot over in California, it's probably cool in Massachusetts. It all evens out. So we don't care. I guess that's kind of like portfolio level NMEC kind of. And so that's how they handled it. Or, this year might be bad, but next year will be a good year. So, it works out. That was their attitude. Just interesting.
I mean, that's all okay by IPMVP. I mean, the whole point of IPMVP is you talk with your customer up front and say, here's how we're going to verify savings, and
absolutely,
that's how we're going to go forward. I would say regulated programs are, one version of that, and they have their own requirements.
Okay, so that's good you mentioned that. So one of the big differences between utility people or utility programs and ESCOs is utilities. There's a lot of people looking over your shoulder, looking to make sure that every dollar is not being wasted or being spent right. There's consultants looking at what the other consultant. One group of consultants does something, a second group of consultants often will look over it, and sometimes even a third group looks over even that. And yeah, I got that. And with ESCOs, it's not so much that. Another question is, the NRE NRA manual put out by Evo. On one of them, it said Oh, one of the things it said was don't use engineering calcs, separate calcs to estimate the amount, the baseline adjustment amount or NRA amount. For example, let's say you put in a server farm, and I know you should really just submeter it, but let's assume you didn't submeter it or weren't able to, and so you just counted up the servers. You can't do that. Let's say you put in a computer lab and you counted up the computers and you knew the number of hours and all that stuff and did this simple one-line calc and say, you know, it's going to use this much per month. And I thought the NRA, NRE manual said that's really what we should try to avoid doing it that way. Am I wrong there, or what do you think?
I don't think it says you shouldn't. I mean, if you're talking about, you know, doing some other inventory and making an estimate of their energy use so that you can adjust your, you know, energy use data before you make a model. I don't think the guide says you don't have to do that. There might be recommendations because, you know, when you're comparing engineering calculations to a modeled approach, you don't know how good one estimate is versus the other. On the modeled approach, we have, you know, more common ways to estimate the accuracy of your estimate using a modeled approach. It's not common practice. There are techniques out there for estimating that uncertainty. And so I think it would be fair if you could estimate the uncertainty of your NRE and your savings uncertainty with both, and then combine it based on, you know, how accurate those models are. We don't have that as a standard practice typically in our industry yet. And that actually gives me a chance to plug the effort I've been heading for the last 4 years with the efficiency evaluation organization, is to make another application guide, this one on stats and uncertainty. So to tell you what the techniques are to, you know, make estimates of measure by measure savings estimates or NREs and NRAs and using a modeled approach, both with option C and with calibrated simulations, option D. So there is an existing application guide, and we're expanding on that in this effort. So I would say we're about 60% through that effort.
Okay, here's one. Is there any particular approach you found effective or let me say that again. What types of impacts to modeling have you seen with individual sites that use solar? Is there any particular approach you found effective for these type of locations? That's actually a complicated question because is solar there before you showed up? Is solar part of the, you know, so that be the base year period, or is solar part of the ECM bundle that you're putting in, or did solar come later? But if you want to give an answer to that.
So generally our approach is you need to understand what the building uses. And so if it uses some meter off the grid, some data, some energy use off the grid, and it has its on-site solar, and there's going to be times when it's pushing energy back into the grid, then you need what's received and what's delivered through the meter and the solar generation data so you can figure out what the building uses. You don't always have that. I've seen some attempts at using, you know, the solar insolation per day as an independent variable in your model and just using the energy off the grid, but I haven't had a whole lot of success with that. You know, I haven't tried it very much. Generally, we've had the energy data that we need, but I've seen attempts like that, and I really can't talk about how successful those are.
Okay.
But that's something you might try, definitely.
Yeah. So for some of you who don't know, and I don't know if you care, but I'm gonna give a 30-second commercial right here. We sell Option C software, and it's used primarily by ESCOs. It's also used by energy managers and a few utility programs, not a lot. And it handles monthly data. It can do weekly, and it can do daily. You know, where you can put in independent variables for, you know, is it a weekday or a weekend, and then you can handle a model. It doesn't do hourly, but it also can handle solar. But solar is really a complicated animal because when was the solar put in? If it's part of the base year, is it something the customer did after the project? So then it's kind of like a baseline modification or non-routine event, or is it part of your ECM package? Or is it part of your ECM package and you don't want to account for it, which happens also. So there's 4 different ways of handling it, and it gets really complicated. There's just so many different Yeah, I'll just leave it at that. But our software does handle that, and that's it for our commercial. Okay, here is another one. So in your regression analysis, do you use a dynamic balance point? I'm gonna read this whole question, and then you can answer. Adjust R squared to compensate for multiple independent variables, adjusted R squared. Do you group your comparisons by ASHRAE climate zones across an enterprise?
Yes, we have multiple independent variables. Yeah, we use adjusted R squared. What was the first part of that question?
That you got the first two. The last one was the one. Do you group your comparison by ASHRAE climate zones across an enterprise?
I think you're talking about a population approach, but mainly we don't do the population.
That's what I was thinking. Sound like you did.
Mainly site level, and there's no, we use the weather for the local climate zone in those analysis.
You do it just like ESCOs do it. You just handle, here's the building, we're going to handle it, we'll do the regression.
Right. What's the gross savings of the building?
Yeah. Okay. Here's one. When creating population groups, do you have filters else? Do you have, sorry, this is a really bad interface here. When creating population groups, do you have filters outside of building type or NICS codes? Do you add filters like size or solar or others?
Yeah, I mean, that's part of your upfront homework when you set up a population program. You want to define what the matching criteria is. So if you're going to define a comparison group of similar buildings, then how do you define similarity? Those are all questions that you can ask. What I've typically seen is location, like zip code or climate zone, size of building, and NAICS code. And NAICS has its problems because generally the NAICS code data we get for a customer is self-reported, and maybe are often the case that the NAICS codes could be in error, not define similar buildings. But yeah, we have to work through those problems to figure it out. But those are the primarily the three that I've seen used.
Okay. How do you integrate utility M&V in California with this CA ISO DR M&V? And for those of us who don't know, can you explain what that acronym means? I don't even know.
I believe you're talking about demand response.
Yeah, it's a DR. M&V we know. CA ISO, I assume that's
California Independent System Operator.
Yeah.
I haven't had a lot of experience. I will say that using this meter-based approach in energy efficiency programs, it's kind of a pathway for integrating these things like demand response. For demand response, you generally want hourly models because you're looking at peak periods, and those are defined over hours of a day, not whole seasons or throughout a season. So, demand response are temporary reductions in energy use, and there's various programs to quantify how much demand reduction there is, and if that goes into an incentive payment or not. So you need an hourly model for that. Yeah. And if you have demand response in your energy efficiency program, they become little NREs that you have to account for.
So with the increasing use of AI and machine learning in developing complex regression equations, is there any concern using optimized regression equations using machine learning compared to the more typical IMT ASHRAE aligned regression equation types?
There's probably a few issues I think the industry has to understand. My understanding, I don't use machine learning gradient boosting machines we don't use those in ours. We stick to the regression because that's practically universally known, and these new methods are, relatively lesser known, have lesser experience. But my understanding is oftentimes machine learning type algorithms will overfit. And so, they'll get you really good accuracy statistics, but when you're predicting it, because it's overfit, it could be wildly off. So you have to be careful of that. You should probably use a lot of out-of-sample testing to test the validity of those approaches. And also, we have this thing about, being able to reproduce exactly model specifications, engineering calculations in the utility world. And, those are statistical approaches using distributions of inputs, and often one model run is not going to get you exactly the same coefficients as the next model run. And so that might introduce some doubt, but really it's not. What you should be looking at is the overall accuracy in those models. But, so I think there's issues like that we have to work through as an industry before we can really say what's the proper use of these more advanced algorithms.
Is maybe well, what you said was very clear, but I'm just going to add something that maybe describes it. When you're doing a fit, maybe you have 12 bills and you can do a linear regression and you get up with a good R-square and a good CVRMSE. But I guess you could use a polynomial fit at second or third degree, and you can get a really great fit, and an R-squared of 0.99 or maybe a fifth degree or whatever. I don't know if it's degree or order. I don't remember those terms. But you know what? They, as you know, when you extrapolate, they just go to the moon or they go to zero. Nice, and then
yeah.
So with these models, I can see that kind of problem.
Yep.
I can see. That's good. That's the end of our questions. Hey, everyone, thanks for coming. Dave, do you have any last points that you want to make?
Yeah, let's use this more. Let's figure out this way going forward, because I think it is, better and more efficient to look at a whole building type approach than get these individual measures and all their problems with it. We didn't even talk about all those issues right now. So we're working as we can, through whatever avenues we can to influence what these rule book requirements are for these utility programs using NVEC. And I would encourage more people to get involved and add their expertise.
Yeah. That's what Steve was saying last time he gave a webinar. It's like, we need people to get involved. Otherwise, people are going to make decisions and not have a lot of experts to listen to. Maybe make bad decisions.
I'd like to get more feedback from the ESCO industry about not only, why they don't use Option C, but what do they think about using things like dashboards, show the owner, what the energy what the energy performance is, and if they use it to manage energy, or if the ESCO does on their behalf or something like that. I think that would be really interesting.
My guess is the reason they might not is because of NREs. And so, they could show that they're saving all this energy, but maybe the client, quit coming to the office, and then they have to go and restate it all. It's like, well, but I thought we were saving energy. You showed it on, we didn't save the energy, or it's the other way around.
Yeah.
I think because you can't do your adjustments in real time, or identify them in real time and then make them, in real time, that they could be misleading using a dashboard. That would be my guess.
Yeah.
Yeah.
That'd be worth a discussion.
Everyone, thanks for coming. Hope to see you next month or next week, and then next time. And David, thanks you so much. It was great.
Yeah, thanks, John. I enjoyed it.
Let's do it again.
Take care, everybody. Okay.
Thank you.
Bye.